Alright, this video is on the combined gas law. Mainly what we're going to be doing is looking at um, the different properties of gases, mainly pressure, volume, temperature, and number of particles or moles. Um, in every single one of those cases, we're going to talk about how they are relating to each other, which I kind of refer to as proportional conditions. Meaning like pressure and volume, they have a relationship, but it's only in certain conditions. We'll talk about what those conditions are. And same thing with pressure, temperature, and number of moles, and pressure and temperature, and all that kind of stuff, all four of them. So we'll take a look at that. We'll talk about and define STP, and then use STP, which is standard temperature and pressure. Use that in an example problem where we're going to break apart how to do one of these problems. Now, there will be other videos online to show the different laws, Boyle's law, Gay-Lussac's law, Charles' law, and Avogadro's law. There'll be different videos there to show you how to do different types of problems. So first, we'll go ahead and take a look at the proportions that you read about. Okay, taking a look at this, we see in the first one, all right, we see that pressure is proportional. Okay, that's what the little fish sign right here is. That means proportional. Okay, and it would be proportional to the inverse of volume. And whenever you have something that is proportional to the inverse, we would say that it was inversely proportional. Okay, and the second one is that pressure is proportional to temperature. The third one is temperature is proportional to volume. The fourth, volume is proportional to number of moles. And then lastly, the number of moles is proportional to pressure. Now, the laws that describe these proportions, okay, we have Boyle's law. We have Gay-Lussac's law, Charles' law, and Avogadro's law. Okay, and they're kind of coupled in here together. Okay, now in order for these laws to be laws, there has to be some conditions. Now those conditions have to do with the other properties that are not mentioned in the law. So for example, Boyle's law deals with pressure and volume. Well, we have to pay attention to the other properties. We have to pay attention to temperature, and we have to pay attention to number of moles. So in truth, Boyle's law is only true, meaning pressure is inversely proportional to volume only if temperature and number of moles are constant. If they're not constant, then we can't really say it's Boyle's law. Okay, we can't say that the pressure is inversely proportional to the volume. Okay, and it's really simple to find out what the conditions are. It all has to do with the other two variables. So for example, in the second one with Gay-Lussac's law, pressure and temperature are involved, which means volume and number of moles needs to be constant for Gay-Lussac's law to work. Okay, same thing with Charles' law. It would be pressure and number of moles need to be constant. All right, and then for this guy right here, for volume to be proportional to number of moles, well, temperature and pressure have to be constant. And then this one right here, your volume and temperature must be constant. Okay. If they are not constant, then we, like I said, we can't really truly fall into the parameters of saying, oh yeah, this is Boyle's law, this is Gay-Lussac's law, this is Charles' law, or this is Avogadro's law. You will have types of problems where only one thing will be constant, but you're going to combine these different rules together in what we call the combined gas rule, which is the focus of this video. Now, what the combined gas law looks like it looks like this. So P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now I know it looks like a lot of variables and it looks kind of confusing, but it's really not, and I'll show you why. Because remember how we were talking about how in order for these proportionalities to make sense, you need to have certain conditions. Okay, for example, if I wanted to look at, okay, so let's say I had, I wanted to know if I increase pressure, what's going to happen to my temperature, right? So if I had a condition, so I'm going to have a before condition, and then I'm going to undergo a change, and then I'm going to have an after condition. Well, the before condition is what we are indicating with the ones over here, the P1, V1, N1, T1. Okay, the change is whatever is occurring. Okay, so like I'm changing, in this case right here, I'm changing the pressure, I'm increasing pressure. And then I want to know what happens, which would be my twos, which is the after the fact. So everything that's to the left of the equal sign is happening before the change, and then everything that's to the right of the equal sign is happening after the change. So P1 V1 over N1 T1 equals P2 V2 over N2 T2. So what we're going to look at here is if I increase pressure, so if I increase the pressure, which I have right here, what's going to happen to my temperature? Now, because I didn't even mention volume or I didn't mention the number of moles, well, I can go ahead and say that those two things are constant. So if things aren't mentioned in a problem, you can make the safe assumption that they're constant. Okay, so what do I do when I have this? I simply cross out the variables that I don't need. So I'm taking away N1 or and N2 and V1 and V2 because, like we just said, they must be constant, which means they wouldn't change. So it wouldn't really have any outcome on the answer. So if I'm trying to find out what happened to my pressure or what happened to my temperature if I increase the pressure, now I could rewrite the equation, right, to look like this. It would just be P1 over T1 equals P2 over T2. Now, how I would set this up if I were you is do a cross multiplication. Okay, it's easier that way. So what you really have here now is going to be P1 times T2 equals P2 times T1. And if I wanted to find out what happens to temperature after the fact, that means I am really trying to find T2. I'm trying to find what happens to the temperature if I do something to the pressure. So then I would just rearrange this algebraically to be P2 over T1, or P2 times T1 over P1. And then I just plug in my numbers that I have in my problem, and I solve. Okay, and your units, make sure you put your units in here. I cannot express the importance of your units while you're doing this because you're going to cancel your units out as you go. Okay, so this is just kind of this was a generic issue right here where I just showed you, okay, this is the equation, so on and so forth, and how to manipulate this combined gas law to do what you want. Remember, whenever you are doing a problem, you're always going to want to have your first step to be to write down this equation, and then when you read the problem, you'll cancel things out as you go, and then it turns a somewhat clumsy equation into a fairly simple one, like this one right here. Okay, so let's go ahead and take a look at an example problem. So I have 1 liter of gas at standard temperature and pressure, and it is compressed to 437 milliliters. What is the new pressure of this gas? So before we get too far, I want to mention this guy right here. Standard temperature and pressure. Standard temperature and pressure, or you may see it as STP, has very unique, specific conditions. Okay, when a gas is mentioned to be at STP, it means it is at 273 Kelvin, and it is at 1 atmosphere. So the pressure is 1 atmosphere, the temperature is 273 Kelvin. You do not need to put the 273.15 or anything like that. Okay? Now, remember, 1 atmosphere is also equal to 760 millimeters of mercury. It's also equal to 101.3 kilopascals, okay, or 760 torr. Okay, I really won't be dealing with pounds per square inch. These are the main ones right here. Okay, so make sure you keep in mind, if it's, say, for example, this question right here is asking about what's the new pressure, I may ask you specifically a unit in that pressure, so you could know, okay, well, what standard temperature and pressure, or what standard pressure in millimeters of mercury? Well, that's 760. Or what is it in kilopascals? That's 101.3. Okay, so you can kind of use those numbers, use these numbers right here as you need to, okay, when I mention standard temperature and pressure, or mainly standard pressure. Temperature will always, 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 always be in Kelvin when you're dealing with gases. Okay, so let's go ahead and take a look at this problem. Very first thing, I want to write down my combined gas law, which would be P1 V1 over N1 T1 equals P2 V2 over N2 T2. Okay, next step I want to do is I'm going to read my problem and kind of see what I'm given. So I'm given a volume in 1 liter. I'm given temperature in 273, so I have a temperature value. Okay, I'm giving a pressure value right here, so I have 1 atm. So I'm also given an additional volume with the 473 milliliters. And then I also have a new pressure, which means that's what I'm trying to solve. So this right here is going to be my x. Okay, that's my variable I'm solving for. So now I have to look at, okay, let's read the problem, find out what is the problem asking me. It's saying if I have 1 liter of gas at standard temperature and pressure is compressed to 473. So I'm taking some gas and I'm compressing it. What's my new pressure? Well, if you see that I didn't change the temperature, which means there must not be a need to have temperature in this problem. Even I mentioned what temperature is, but there's no change involving the temperature. So we're assuming that temperature is constant. So we're going to get rid of it. It's not involved in the equation. And then, like I also said, if it never mentions anything about number of moles, which most of the time the questions won't, then that must also be constant. So now I have V volumes and pressures. So now I need to assign my V1, P1, V2, and P2. Well, I know my P2 is my X, my second volume, and my first volume, and my first pressure. So my first volume was 1.00 liters. My first pressure was 1 atmosphere, right, because that's standard pressure. And then my second volume is 473 milliliters, but, okay, if you can, always convert your volumes to liters, which means it would be 0.473. And yes, I want you to show that via dimensional analysis. So if I was to rewrite out this law with now or this equation with the variables filled in, then I end up with this guy right here. I will then cancel out or divide by 0.473 liters to get my x by itself. In doing so, you see that my liters will now cancel out, okay, which they will over here as well too. So now all I have left is atmospheres, which is a unit of pressure. My final answer ends up being, okay, 1 divided by 0.473 is 2.11 atm equals x. Now, one thing I forgot to mention is that standard pressure is actually 1.00 atmospheres, not just 1 atmosphere. So that's why I have 3 sig figs.